Okay, in this video we're doing Calc AB problem set 108. The problems and playlists are in the description below. Let's do it. Find the average value on 0 to pi over 8 for f of x equals 1 over 1 plus 4x squared. All right, average value is integral divided by interval, so I'm going to set that up. So it's the integral from 0 to pi over 8 of 1 over 1 plus 4x squared dx all over pi over 8 minus 0, so over pi over 8. So since you're dividing by pi over 8, I think it's easier to think of it as multiplying by 8 over pi. So I'm going to write equals 8 over pi, the quantity. We have to integrate this thing. So I look at it and it's like, if I try to make u equal the entire denominator, 1 plus 4x squared, I don't have any x's in the numerator. So then I have to think like, all right, well, what could it be? What has a quadratic in the denominator? It's arctan, right? So this is going to be arctan. For it to be arctan, it would be 1 over 1 plus u squared. So u must be 2x. Which means there should be a 2 in the numerator, but to balance that, I'll put a 1/2 on the outside. So now this is perfectly arctan. So hopefully if you've been doing all the problem sets and practicing, you're getting to the point where you can kind of do that on your own. If not, just do the u substitution. U is equal to 2x, 1/2 du is equal to dx, and go from there. But I have it balanced out, so I'm going to say this is the 1/2 stays, and it's a perfect arctan, so arctan of 2x. And then we're going from 0 to pi over 8. At this point, I realize I think I wrote the wrong problem. I don't really know what I want. I probably wanted 0 to 1/2. Was probably like in my dreams what I was doing. But it's fine because the domain of arctan is all real. So like any number would have worked, but this isn't going to look nice. So 8 over 2 is 4. So we have 4 over pi. The quantity, we're going to plug in pi over 8, and we get just the arctan of pi over 4. Which I'm pretty sure I wanted to be the arctan of 1 because the arctan of 1 is pi over 4, but mistakes were made. That's okay. Minus the arctan of 0. Arctan of 0 is 0. So this does simplify to 4 over pi and then arctan of pi over 4, which got me like wondering about all kinds of arctan situations, right? Because we have pi over 4 and 4 over pi. But anyway, that's the answer. So pi over 8 does work. It's in the domain of arctan, but like I'm thinking it was a mistake. I'm thinking I meant to do almost certainly 1/2 because that would have given me the arctan of 1, which is pi over 4. Whatever, doesn't make a difference. Problem works. So that's the average value of that function on that very weird interval. All right, next up, use the values, differentiable function f. To answer the question. So approximate the integral from 1 to 10 with a right Riemann sum. We've done this a million times at this point. So just don't forget the approximately equal to sign. Integral from 1 to 10, f of x dx is approximately. From 1 to 4 is 3, and then the right endpoint is 3. From 4 to 6 is 2, the right endpoint is 5. From 6 to 9 is 3, the right endpoint is 8. And 9 to 10 is 1, the right endpoint is 7. You should leave this on the AP exam, but I'm going to simplify it anyway and risk it. I got 50. All right. If g of x, so this is b, if g of x is x squared times f of x, so this is a little different, approximate the integral from 1 to 6 of g of x dx with a left sum. Okay, so what I like to do for this, there isn't really space on the table, but I usually like to add another row to the table that is just the values of g of x. So what I'm going to do instead is kind of like create my own table. So 1, 4, 6, 9, 10. After doing that, I realized I don't need 6, 9, and 10 because I'm doing a left sum, but it's totally okay. All right, so we're supposed to do x squared times f of x. So at 1, x squared is 1 squared times f of 1. So that's 1 times negative 4, which is just negative 4. At 4, we get x squared is 16 times f of 4, which is 3. So 16 times 3 is 48. I did 6 because I didn't really read the problem. X squared is 36 times f of 6, which is 5. 36 times 5 is 180. We're not going to use that value. We don't need 9 and 10, so I'm not going to do them. We want to approximate the integral from 1 to 6 of g of x dx. So using a left sum. So from 1 to 4 is 3, and then the left endpoint is negative 4. And then from 4 to 6 is 2, and the left is 48. And so when we add, you get 96 minus 12, so you get 84. So that type of problem is not like crazy common, but like it shows up where you have to kind of like work with a table to create values for another function and then use your values that you created to approximate an integral or think about the fundamental theorem or whatever. All right, so new problem or new part of the problem. Use the table of values for the differentiable function. Oh, yeah, same thing. Prove f prime of x equals 1 for some x between 1 and 10. So since this thing is only differentiable and not twice differentiable, there's got to be some interval where the slope, the average rate of change, is 1, so that we can use the mean value theorem and just kind of go from there. So if you look at the table, from 1 to 4, you go up 7 and over 3. That's not it. From 4 to 6, the change in y is 2, the change in x is 2, so that would work. And then also from 6 to 9, you go from the change in y is 3, the change in x is 3. So that interval would also work. Either of those is going to work for you. If the function was twice differentiable, we would be able to prove that f double prime is equal to 0 somewhere, because we can prove f prime equals 1 on 2 separate intervals, which means f prime, at each of those values, the slope of the secant line through those 2 points would be 0. But that's not the question, so I don't know why I'm talking about it. But like, just think about it, you know? All right, mean value theorem. So we need this function to be differentiable. It is differentiable. Differentiability implies continuity, so we're good to go. By mean value theorem, I'm going to use the first interval. F prime of c is going to be f of 6 minus f of 4 over 6 minus 4, which is going to give you 2 over 2. And that's definitely 1. And that was kind of the point, right? And so then for some c that's an element of 4 to 6, and then I never know because it said 1 to 10, so then I'm going to say therefore for a c between 1 and 10. I don't think that step's necessary, but I always do it just in case. All right, next up, calculator question. Good. We are given that f of 2 is 15 and f prime of x is e to the cosine of x squared. We want to approximate f of 2.1 with a tangent line at x equals 2, and then also find f of 2.1. So this is an approximation versus finding the exact value. So the tangent line, I'm gonna use a calculator for everything. So I've defined the function. I always call derivatives d, whatever the name of the function is. So df of x is e to the cosine of x squared. So df of 2 is 0.520147. The tangent line then is going to be rearranged. So 15 plus the slope times the quantity x minus 2. So I plugged in and I got 15.052. Here's what I would write down, I guess. F prime of 2 is 0.520. Because 3 decimals always, unless otherwise stated. So I'm going to write that. You could also do more than 3 decimals if you're uncomfortable with that or you're not sure how to round or whatever. The tangent line then is going to be y minus 15 is 0.520, quantity x minus 2, and then f of 2.1 is going to be 15.052, approximately. The approximately equal to signs matter, in my opinion. Well, definitely for f prime. Sorry, for f of 2.1. F prime of 2, I don't know. I think you could probably write equals, and that would be kind of okay by their standards, but not by mine. All right, I need to find the actual value. I have the derivative, and I know the value at 2, so I think I can just use the fundamental theorem. So I'm going to do 2 to 2.1 of f prime of x dx should be, by the fundamental theorem, f of 2.1 minus f of 2. And if you think about it, the calculator can do the integral. We know what f of 2 is, so I'm going to rearrange this. We'll get f of 2 is f of 2.1 is f of 2 plus the integral from 2 to 2.1. So it's like the value you know plus the displacement from 2 to 2.1. And then here's what the calculator said it was, 15.062. So they're pretty close, which you would expect because tangent lines approximate functions and give close values, especially if the point of tangency and the approximation point are close to each other, which they are in this case. So I think this is good. That's the end of the problem set. I hope this was helpful, and good luck.